All right, let's get rolling. Welcome back to Data 100. Today we're going to be talking about cross-validation and regularization. Okay, so as a reminder, homework 5 is out tomorrow. Homework 5 is out and due tomorrow. Homework 6 will be released tomorrow, and it'll be due Tuesday. If you noticed the screencast yesterday, my video got frozen somehow, but the audio is there. So if you want to leave a comment on that YouTube, like if you're watching it yourself and you're going through the whole thing and you want to help out a fellow student or help yourself at least, you can leave a comment on the YouTube video with like the slide number and the time that in the video with the slide number. And if you do that on the YouTube video, then I'll update that YouTube description so that if you go back to the video later on, you can just click around in the description to get from place to place in the lecture. So if you're watching, I recommend if you're watching it yourself and you want to like record it down for yourself, it might be good for you and it might be good for other students too. Okay, but I really hope the video works today. I tested it out and it seemed to be working, so we'll see how it goes. All right. So right now we're at the point in the class where we're getting ready to expand our repertoire of models. So far we've talked about a linear model, a simple linear model, a multivariable linear model, and then we talked about how to perform feature engineering in order to model more complex relationships. We talked about polynomial features yesterday and one-hot encoded features yesterday. And as the class progresses, we're going to learn about more and more variants of models and more like tuning parameters that you can have on those models. One of those tuning parameters is called regularization, which we'll go over today. But the main question with all of these model tweaking is a question of how do you pick the best model among many models? And that is the purpose and the goal of cross-validation. Okay. As I mentioned yesterday, in Data 8, we learned this technique where you take our original sample, you split it up into a training set, a validation set, and a test set, and then you compute 3 separate errors, right? You compute, for any given model, you can compute the training error, and the validation error, and the test error. And we use a training error to fit the model, right? So to fit the model, we tune the model until it gets the lowest training error. The validation error we use to choose a model. Okay, so if we have 10 competing models, we'll fit them all in the training set and then choose the one with the lowest validation error. We mentioned yesterday how the training error can mislead us. Right? The training error can be artificially low, especially as we increase the complexity of our model, because the training error only reflects the bias of our model. It does not reflect the variance of our model. Okay, and this test error we use to report the final accuracy, and in general, it's best practice to keep that test set locked away in some vault somewhere, so you don't even have the opportunity to peek at it. There have been a lot of peeking at the test set generally has bad consequences, and you may have seen some of those consequences if you've looked at some of the difficulties that people have had in science replicating each other's papers. Okay, so here's a diagram. And another way of looking at these 3 types of errors is that the training error, the training set we use to minimize the empirical risk. Okay, so the training set or the training error reflects the empirical risk on that particular training set, whereas the validation set makes an estimate of the population risk. The reason why it makes an estimate of the population risk is because we're simulating with the validation set data that our model has not seen before. Okay, so I used the analogy yesterday of studying for an exam, and if you take exam A and then you take exam A again, you might think you're doing really well, but in reality you might just be overfitting to that particular exam. And a similar thing is happening here, where you'll want your validation set your model has not seen before, and so that's an estimate of our population risk. Okay. And our test set here is what we call a quote-unquote clean estimate of the population risk. And the reason why it's clean is because it's data that we have never used for anything else. And so even the validation error can be artificially low, because what we're doing is we're peeking at that validation error to pick some models, and since we're picking the model with the lowest error, that error is generally lower. That error is generally lower than the test set error as well. Okay, so from lowest to highest, generally speaking, we'll have training error is the lowest, validation error is the next lowest, and test error is the highest. Okay, so again, for model selection, if we have these models here, I've labeled them 1 through m, they can be anything you want. Okay, so we might have f1 as a linear model, we might have f2 as a degree 2 polynomial model, maybe f3 is a linear model with fewer features, right? We talked about removing features and how that can reduce your variance, so on and so forth. So you can imagine that f1 through fm are any set of models that you want to choose or you think might be good on this data. Okay, our procedure here is you fit each model to the training set, compute the validation error for each of them, pick the model with the lowest validation error, and this is how we perform model selection. Okay, so by model selection, I'm referring to the process of having a bunch of models and picking one of them as our final model of choice. And then we can report the test error of the model that we've chosen. Okay, so this is all well and good. And what we're going to do now is we're going to focus on that validation error, and we're going to give it an upgrade. Okay, so the upgrade is what we call cross-validation, and what we're going to be talking about today is what we call k-fold cross-validation. The intuition behind k-fold cross-validation is that if you have a held-out validation set, so if you split apart your data and have a validation set, usually your validation error will be close to your true risk, but sometimes it won't be. Sometimes you can just get unlucky with the way you split apart that data, and so you have some variance in your validation error. Okay, so the validation error is trying to estimate the population risk, and sometimes you're going to get some variations around the estimate because of the randomness of the sample. Okay, so sometimes you get unlucky, and the idea behind cross-validation is try to mitigate some of your unluckiness by computing multiple validation errors for the same model. Okay, so the idea is if you make 5 validation errors per model, then chances are the variability in your validation error will kind of even itself out. Okay, so even if you get unlucky on one trial, the other 4 trials will hopefully balance out that one bad one. Okay, so here's the idea. In k-fold cross-validation, we're going to start by setting aside a test set, and then we're going to split the rest of our sample into k equal size partitions. Okay, so we're just splitting up our sample into k splits or k folds. If we're performing 3-fold cross-validation, then we'll split the rest of our sample into 3 parts. Okay, now we have 3 splits, and we're going to use k minus 1 of them to train our model, and the last split as our validation set. Because we have k splits, we can repeat this procedure k times for every partition, and the average of those k errors is our validation error. Okay, so I'm going to show you a diagram. Hopefully it'll be a little more clear after this diagram. Okay, so here we go. Here's 3-fold cross-validation. I have my sample. I split apart my test set, and now I have fold 1, where I've taken the first segment in my sample and called it the validation set. Here's fold 2, where I take the second segment of my sample and call it the validation set. Here's fold 3. Okay, so this is one sample, and I've split it up into 3 parts, and then for every fold, I'm taking the first third, the second third, and the last third as a validation. Okay, so by doing this, I'm training my model 3 times, and I'm computing 3 validation errors each time on this blue validation set here. Okay. And the idea here is that by doing k-fold CV, you get more than 1 validation error per model, and that lets you capture some of the variability in that validation error. So you repeat this process for every model that you want to try out. So if you have 10 models and you're performing 5-fold CV, you're going to compute 50 validation errors, right? Because every model you're going to compute however many folds you have, it'll be that number of folds per model. Okay. And so in practice, we usually choose k to be 5 or 10. Generally speaking, so there's many variants of k-fold cross-validation. So you can imagine instead of splitting apart the sample into like 5 parts, you split apart your sample into like many, many, many small parts, and that's what we call leave one out cross-validation. If you choose k to be equal to 1, then you essentially have, or 1 or 2, then you, roughly speaking, have the same held out validation set that we had before. And so generally speaking, like we think that the best k is usually around 5 or 10. Okay, so the advantages of k-fold cross-validation is you make more use of your data for training. So with this sort of cross-validation, you're taking your entire sample after you split apart the test set, and you're using every point in your sample at least once to train your model. And since data are often scarce, using k-fold CV can be a good way of like at least making more use out of the data that you have. Okay. The main reason why we like k-fold CV is that if you have repeated estimates of the validation error, you have a better sense of whether your validation error you got unlucky or whether you're really capturing the average validation error. Okay, and in particular, because you have multiple estimates for every model, you can create confidence intervals for that validation error. Disadvantages, as you might have imagined, is that it's more computationally expensive. Okay, so if you're essentially multiplying the time it takes by a factor of k to train your models, because for every model you're going to be fitting k validation sets to, or you're going to be fitting k training sets to. Okay, so for models that are complicated or hard to fit, this might take more time. Okay, so there are more advantages and disadvantages, but these are the main ones. Okay, so for practical purposes, these are the ones that I want you to remember. All right, let's take a look. So I have here some traffic data. And what I've done is I've done some pre-processing on this traffic data. So I have here the traffic volume, which is what I'm trying to predict. And this is for freeway in Minnesota. Okay, and these traffic recordings include weather and holiday features from 2012 to 2018. So we have about 6 or 7 years of traffic data. And we have 48,000 rows, and we have 28 columns. But you'll notice that after the first 4 columns or so, all the rest of the columns are hour. Okay, so what I've done here is I've one-hot encoded the hour column in the original table. Okay, so I have hour of day as a one-hot encoded column. Okay. And what I like to do is predict traffic volume using the rest of the columns, or using the rest of the data that I have available. Okay. What I'm going to do is show you how to perform k-fold cross-validation. And it's not super hard because scikit-learn has it built in. So what I'm going to do is first, scikit-learn, I'm going to first separate out my test set. So here is the train test split function, which essentially just randomly splits apart my sample into 2 parts. Okay, so I have x test, y test. Here we go. And then for my x matrix, I want to take everything after the first column. So here is everything after the first column. For my y vector, I want just the first column itself. There it is. And let's say that I'll split apart 10% of my data as my test set. Okay, so there we go. And here is my x. Okay, so we see here we have fewer rows than we had before. And these rows come in a random order. All right, and what I'll do is I'll just reset the index for all of them so that we don't have to deal with these weirdly ordered numbers. So here we go, x.reset index. Let's do that, and then do that for my y's as well. Oops. like so. Okay, so here we go. Here's my x. This is my sample, and I have a test set that I'm not going to use until I'm done. Okay. Now the way to perform k-fold cross-validation in scikit-learn, there are actually multiple ways of doing it. One of the simpler ways is to import what we call this k-fold transformer. And a k-fold transformer works pretty similarly to the rest of scikit-learn's transformers and classifiers. So we'll have k-fold, and here it is. So I've initialized what I have here, initialized a k-fold, and what I can do is do k-fold.split on my x matrix. This will give me an iterator of the different folds that I have, so I can iterate over this generator here for train indices, and what it will do is it will give me two sets of indices, like so. It will give me the train indices first and the validation indices second, and it'll do that 3 times because I've asked for 3 splits here. Okay. So to get out the first training set, I can call xtrain xvalid equals x.iloc, and I'll pass in my train indices x.iloc and pass in my validation indices. So pretty simple. Here's y train, here's y valid, and again, I just have to do y here. Okay, and that's pretty much it. So what I've done here is I've split apart my data into 3 folds, and for every fold, one of the folds will be marked as the validation set. Hold on, yes, this is right. One of my folds will be marked as a validation set, and the other 2 will be marked as a training set. To show you what that looks like, I can display a few rows from x. I'm just going to display like 3 of them. So I'm going to do that. Okay, so we see here on the first iteration of k-fold, I'm going to have these rows. I'm just showing you like every 12,000th row, just to avoid some big tables. But the real X train has many more rows than this. It has 2/3 of the number of rows it had originally. Okay, so here's my first split. It has these 3 rows. The second split contains these 3. The third split contains these 3. So you can see here that each split has a different set of rows, and we're going to use each split to train a model. Okay, so you can imagine me filling in the rest of this loop. I can create a linear regression linear regression model, and I can fit it to x train and y train, and then compute the validation accuracy on x valid and y valid. Okay. In reality, you won't often use this k-fold transformer. And if you really want to understand what it's doing, you should implement it yourself to try to get a feel for how to implement these things. But in practice, what you'll most often do is, let's see here. What you'll most often do is import something like this cross-validate function that scikit-learn comes with, and that will do the k-fold cross-validation for you. Okay, so what I'm going to do is I'm going to implement a few feature engineering like transformers, and I want to compare the performance on this particular data set. Okay. The first type of transformer I want to do is simply dropping some columns from X. Okay. The second transformer I want to do is the polynomial regression that we saw yesterday. So here I'm going to do polynomial features, and I'm not going to include the bias. And then here I want to do a linear regression after we do polynomial features, like so. Okay. To make a pipeline for the model with fewer columns, I can keep this mostly the same, but replace the polynomial features here with what we call a function transformer. And the function transformer takes in a regular old Python function and turns it into a scikit-learn like transformer. And I want to make sure that we pass in these columns into this function here, like so. Okay. So what I can do now is show you how this cross-validate function works on a simple linear regression. All right, so here, I'm going to create a polynomial model, but only ask for degree 1 features, which doesn't do anything to my original matrix. Okay. To compute the scores, I can call cross-validate with my model, give it my training or my sample, and I'm going to ask that it use the negative mean squared error. This just happens to be built into scikit-learn, but I could also pass in my own function here if I wanted to compute the mean squared error. And I'm going to ask for 5-fold cross-validation. Okay. Let me show you what the scores looks like. Okay, so scikit-learn automatically splits apart my data into 5 parts. So I notice I didn't pass in an X train or Y train. I passed in my whole sample without the test set. And what scikit-learn does is it takes the sample, splits it up into 5 parts, and does a k-fold cross-validation for each part, which gives me an array of 5 mean squared errors. Okay, so to grab out these mean squared errors, sadly it does put a negative sign in front. So what I'm going to do is take, the negative scores, grab the test score attribute, grab the mean, and there is the validation error for a multivariable linear model on this data. Okay. I'm going to throw this function into, I'm going to throw this line into a function here so I can call it over and over. So I'm just going to take this, pass it in here, and that's good. All right. And then I'm going to take this line right here and throw this into a function as well, like so. Okay, so I'm just taking some code that I manually wrote, and I'm putting it into some functions so I can reuse them later. Okay, and the reason why I want to do this is because I want to try out a bunch of models. All right, so let's make a column with our models, and let's say that I will make a model with just the first column of our data. I'm going to make a model with the first 3 columns of our data. I'm going to make a model with the last, I'm going to make a column with numbers for columns number 4 through 27. Okay, so the reason why I'm choosing these numbers is because if you look at my X data frame here, okay, so the mini model function here creates a model that only uses a temp column to predict the traffic. The second model here uses the first 3 columns. And the third model here uses all the hour columns, but none of the other columns. Okay, so I'm only using subsets of my original columns of X. And then, as usual, I can do some polynomial models as well. So here's a degree 1, here's degree 2, like so. So I have here 5 models I can try out against each other. Let's give them all names. So here's a name of each one. I'll call the first one mini 0, mini 0 through 2, mini 4 through 27, and then here's here's a linear model, and then here's a poly with degree 2. Okay, so 5 models. I've just put them in a data frame so it's easier to display. Okay, so you can I can kind of show you, like, here's the first model, here's the second model, so on and so forth. Okay, so I'm going to take my models and apply the CV function, which does cross-validation for everyone. Save that in that column. And then I'm going to compute validation errors for each model. So take that, cv.apply validation error. Let that chug along. So it'll take a little while because it's fitting 5 models for every model. So it's doing a total of 25 fits. And here we go. Okay, so I have the validation error for each model. And in this CV dictionary here, I have like 5 validation errors total, and here is the mean validation error. All right, so it takes some work. But you can like get out all these errors here and plot them. So what I'm doing here is I define some functions for plotting, and I can call them. So let's do errors equals make errors here. And I can plot them. So here is a plot. Well, here's an error. Oh my gosh. What happened here? Oh, I forgot to include a parameter. My bad. Forgot to include a parameter here. Let's do take a look at documentation here. I want this. Okay. Okay, let's try this again. All right. Let that go. Oh my gosh. What's going on? I'll have to let this run. There we go. So now it's fitted, and now I can plot. Could have sworn that worked. Okay. I'm gonna do some hot debugging here. Okay, so, oh, I see. I changed the line here, but not the function. All right. Do apologize. By the way, as a nifty trick, if you notice the cell is taking a while in Jupyter to run, you can type in %time and run it, and that'll record down the cell, like how long that cell took to run. So in the future, if you rerun that cell, you can try to like, if you know the cell's going to take 5 minutes, you can like start that run, go get a coffee, and then come back. I often do that. But in this case, I've like kind of limited myself to some simple models so I can show you during lecture. Okay. But oftentimes I will include this line here. Okay, check that. Okay, so we are good now. Let's really cross my fingers this time. Okay, here we go. Okay, so we see here that we go from simplest to more complex, right? So we have here, here's a training error, and I've shown you the training error for the model with the first column, the model with the first 3 columns, the model with all the hour columns. Here's a linear model with all the columns available in the original matrix, and here's a model with degree 2 polynomial features. Okay. I can also show you the validation errors. So here's the validation errors. I'm going to change this. I want to do a log scale, and I want to show you the validation errors. Okay. So what do you notice about the validation errors? We notice that the first model has some validation error. The second model has some more validation error with more variance. The model with just the hours column seems to be doing pretty well. And in fact, it does better than the model with all the columns. Okay? And the model with all the columns not only does worse in terms of validation error, but has a higher variance in those validation errors. And this degree 2 polynomial model has the lowest training error as we expect, but it has the highest validation error, and in fact has like a huge variance here. This is a log scale, right? So every time I go up by 1, I multiply by like 3, roughly speaking. And so this right here is like orders of magnitude more variable than the linear regression model. Okay. So if you have models to test out, you should be able to make plots like this. And if I give you a plot like this, you should be able to conclude, okay, what's the model that I would pick? I would pick this one because it has the lowest validation error. Which model has the highest variability or highest variance? The polynomial 2. And in fact, non-intuitive, perhaps the less intuitive result from this demo here is that by dropping columns from my original table, I actually do better than keeping all the columns. Okay, so it turns out that you can use cross-validation to see the bias, variance, and risk of a model. So the training errors show you the model bias, more or less. And the validation errors, these points on this plot here, show the risk, roughly speaking, so they're estimates of the risk, and the confidence intervals here show you the model variance. Okay, so we can get it all through cross-validation. It's a good technique. Let's take a break. All right, go for it. Okay, let's bring it back. Let's talk now about a technique that we call regularization. The idea behind regularization is that when you have complicated features, oftentimes your model will give those complicated features large model weights. Okay, but when you have large model weights, you in general have more complicated models. So here I have a degree 2 polynomial, and here are the coefficients for this degree 2 polynomial. They're quite large because this water flow attribute is like 1 times 10 to the power of 12. So this is like water flow in like gallons for like an entire reservoir. So this reservoir has like tons of gallons of water. So these coefficients here are pretty large to match. Okay. I fit a degree 12 polynomial to the same data. And right here, what I want to show you is I have here a table of the coefficients. And in particular, the coefficients for like the 4th and 5th polynomial degree are quite high. And so you can imagine that if I change x by like just a little bit, right? If I change x, if I just nudge x a little bit, I'm going to get like vastly different predictions because of these large coefficients here. Okay, so in general, if you notice that if you can nudge x a little bit and get really different predictions, it's probably a sign of overfitting. And in this case, another way of diagnosing the overfitting is that the coefficients here for the higher degree polynomials are really high, and in fact higher than the rest of the coefficients. Okay, and so the idea is that we can have smaller, we might want to use the polynomial features, but we want to tell the model not to avoid putting larger model weights on these high degree features or on the features in general. Okay, so the idea here is if I can make these numbers smaller, my model gets simpler. But I can still make use of the higher degree polynomial features without causing overfitting. Right, so you can imagine here that I might want a little bit of a degree 3 polynomial in here to make it fit a little better. I might want a little bit of a degree 4, but maybe not too much of the higher degrees. Okay. And so the idea of regularization is we'll change our loss function to add a penalty for model weights. So here's the MSE loss with what we call L2 regularization. The loss function is here, but you'll notice that this part right here is the same old loss that we had as before. Okay, so this section right here is the same loss. Nothing has changed from the mean squared error loss that I've shown you before. And all we've done to this loss is add this term right here, which we call the regularization penalty. And you'll notice that this term right here depends on the values inside theta itself. Okay, so if my model weights are large, then this penalty here will make my loss high. If my model weights are small, the penalty here will be small. And if my model weights are all 0, then I'll have no regularization penalty at all. Okay. You'll also hear the term shrinkage. And when people say shrinkage, it usually means that they came from a statistics background. But for us, regularization and shrinkage mean the same thing. The idea here is that the reason why we say shrinkage is because we're trying to shrink our model weights to 0. Regularization has a more sophisticated origin. That's to do with the fact that by adding this penalty here, it turns out that we're going to make our matrices regular or invertible. Okay, but that's kind of an aside. You don't have to know that. You just have to know the name. Okay, so what we're doing here with regularization is we're saying, okay, I do want to minimize my loss on my data, but I want to do so without making my model weights too big. So now we have a balance between fitting our models to our data points, but keeping our model weights small, or we favor simpler models. Okay, this lambda here is called the regularization parameter, and it's a non-negative constant. Usually relatively small, but it depends really on the data that you have. Okay. And so I can talk to you about what we call ridge regression and lasso regression. Ridge regression just means take our linear model and slap on the L2 regularization. Okay, so linear model loss, so here's a linear model, here's the L2 regularization. If we use a linear model with this loss function, then we'll call it ridge regression. We call this, the reason why we call it L2 regularization is because we call this right here the L2 norm of a vector. You don't really have to know what that means, but roughly speaking, the 2 here refers to the fact that we're squaring every element. You might see like L3 norm or L4 norm, and roughly speaking, that means that we'll take the cube or the 4th power of every element. Okay, so lasso regression is a linear model with what we call L1 regularization. Same loss, same model. Only thing that changes is this penalty here. And instead of squaring every theta, we'll take the absolute value of the thetas. This is what we call the L1 norm. If you take a more advanced linear algebra class, you'll learn all about these norms. They come up quite a bit. Okay, I'm going to show you how these work. Here I have data on water flowing out of a reservoir. So what people have done here is they measured how much the reservoir water level changed, and they also measured how much water they actually flowed out of the reservoir, and this is in millions of liters or something like that. But what I've done here is I've made them smaller just so they're easier to see and work with. Okay, but the pattern is the same, right? So here I have the water level change, and here's the water flow. We'd like to predict water flow from water level change, and so what I've done here is I've created data matrices as usual, x and y, and I put water level change in my x matrix and water flow in my y vector. Okay, to implement a ridge regression model, I can import the model. Okay, so you'll see that as a pretty common theme. We can talk about complicated models, but most of the time they'll be implemented in scikit-learn, so we can just use the built-in one. And so if I scroll all the way back up here to the polynomial model, here it is. I can copy that, scroll back down, and paste it. Copy paste coding. What more can you ask for? Okay. I replace the linear regression with ridge, and I'm basically done. I do have some parameters I need to tune, and I won't go into the details now. But here in scikit-learn, they call the regularization parameter alpha. But on our slides and in the textbook, you'll see lambda. Alpha and lambda are used interchangeably, but we've already used alpha for gradient descent, so we won't use alpha in our class. You'll just have to remember that for scikit-learn, the parameter is called alpha. Okay, and then we're going to normalize. And we'll go into why we have to set these parameters real soon. But let me copy this and do the same thing but for the lasso model. Let's see here. I have to adjust the tolerance. There we go. Okay. I have here some functions to plot the predictions from a model. Not too important for today. But here, what I can do is call my plot models function with some models. Okay, so what I'm doing now is I don't want to actually show you these yet. I want to compare a polynomial model with degree 12. So I've saved the degree in the degree variable. Here it is. With a ridge regression model of degree 12. Okay, so both of these models are linear regression, but one of them, the ridge regression model, has a penalty. And what we notice here is that because of the regularization penalty, the model favors smaller model weights, and because of that, we get a smoother curve through the data because it's not making as much use of the higher degree polynomial features. Okay, so polynomial model on the left, polynomial model with regularization on the right. Okay, let me change the degree to 5, show you how that looks. So if I only use degree 5 features, both models look kind of the same, but the regularized model looks a little bit smoother. Okay, I want to show what the alpha or the lambda parameter does for regularized models. So I'm going to make a new variable, change back to 12. Let's set alpha. Let me make some ridge regression models. And for the first one, let's set alpha to be a small value. Here's 0, 0, 1. Here's 0. Let's do 0.1. Let's do 10 here. And let's do 100. So by default, the alpha is 1, but almost every time you'll want to tune that alpha. So let me show you what changing the alpha or the lambda does. And so it'll fit the data. Okay, so from left to right, we have small, not as small, bigger, and then very big. And what do you notice happen to our model? When alpha is very small, or when lambda is very small, we don't have a large penalty for model weights. And so what that means is the model will want our model weights to be small, but it won't care that much. It will still let our model fit basically the same basically the same model weights as it did before. So we see here some wiggles and this curve going up like this. as we increase alpha, the model becomes smoother because it favors smaller model weights. But if you increase alpha too much, it might become too smooth. Okay, so if we do that, the line doesn't really fit our data anymore, and that's because our model wants the weights to be really, really small. Okay. Let me show you. Let me compare the ridge regression model with the lasso regression model. So here I'm going to set alpha back to 0.1 here, and I'm going to change this to lasso, like that. Okay, so they look basically the same. So the fitted curve here for ridge regression and lasso regression looks roughly the same, and we can interpret that as saying that ridge regression and lasso regression both have about the same penalty here for model weights. But there are some subtle differences between the two, and we'll go over in more detail those differences real soon. Okay. Actually, I'm going to show you a little bit right now. So let's take a peek. So what I've done here is I have some functions that will just display for me the coefficients of models. And what I'll do here is take some degree 12 polynomials, and I'm going to take the regular polynomial model, fit it to my x and y, and just show you what that looks like. Okay, so this the function coefs here just displays the coefficients of a fitted model. And what I can do is call this the polynomial model, and I want to display it. I want to make sure we get all the rows, like so. Okay, so these are the coefficients for the polynomial model. Let me do the same for the ridge regression model. There we go. Let's call it ridge. And I'll do the same for the lasso regression model. Okay. So we saw before that the ridge regression model and the lasso regression model create roughly what look to us like similar curves. And what we'll notice here is that if you compare the polynomial model weights with the ridge regression model weights, the ridge regression model weights are in general much smaller. Right? So we have here for higher degree polynomial features like 5 and 6, the ridge regression model weights are like 100 times smaller because this is e to -6, this is e -8. Okay. On the other hand, the ridge regression has larger model weights for smaller degrees. It's a little bit hard to see, so I'll plot them in a second. But what I do want to point out to you is that for the lasso regression model, notice how all these weights are 0. Okay, so the ridge regression model has a lot of really small weights. This is like 7 to times 10 to -19. And the lasso regression model sets it equal to exactly 0. Okay. I can plot these coefficients. So change the display to a plot call. And what I've done here is I've taken the model weights, put them on a log scale, and I'm displaying them as we go for each of the degree feature. Okay, so here's like x to the power of 6. Here's a coefficient for x to the power of 12. And we see here that the polynomial feature has, roughly speaking, higher model weights than the ridge regression. Okay, so a difference of like 2 or 3 on the log scale is a difference of 100 or 1,000 in real numbers. And in particular, the lasso model has model weights and then they disappear. And the reason why they disappear is because they're all 0. So anytime you don't see a line connected here, the lasso regression model has set the model weights to 0. Let me decrease alpha so we get less regularization. Like so. So I'm changing alpha from 1 to 0.001. And we see here that, again, the polynomial feature model weights are relatively high. The ridge regression model weights and the lasso regression model weights are roughly equal. but the lasso regression has set a bunch of model weights to 0. So all the discontinuities you see in the green line here are where the lasso regression model set the model weights to 0. Okay. So here we go. Let's dive in deeper into this regularization. And in particular, I'm going to ask you several questions for you to try to feel out what regularization is doing. The reason why I'm doing this is because you can memorize. Okay, so you have kind of like two alternatives for keeping track of all the knowledge in this class, right? By this time, you may have noticed that we just have a ton of details to go over. Like you saw me give a long list of bias variance trade-off things. There's like all the pandas functions to like kind of remember or keep around. There's the SQL things to keep around. Okay, and so one thing I want to do for you is try to get you to not have to memorize as many things, like getting you to try to toy around with these equations yourselves, so you can so the equations will make sense to you rather than the equations just being a list of collected facts. Okay. And the way you create that mental framework for yourself is by asking yourself the what if questions. And so here we have L2 regularization, L1 regularization. Lambda, I've mentioned before, is a regularization parameter. And so we see that higher values penalize model weights more. And what I want you to discuss is what happens if lambda equals 0, what happens when lambda equals infinity, and does this change between L2 and L1 regularization? Okay, so questions like these are like super fair game exam questions. I could just ask you something. I could ask you these questions straight up and give you a multiple choice, and you should be able to answer it. Okay, so think about it and discuss it with your neighbor for 2 minutes. All right. So what happens? Lambda equal to 0. Any guesses? I will take 3 volunteers, 1 for each question. What happens when lambda is equal to 0? And I'll write down what you say. So what you say will be immortalized on these slides. If no one says anything, I might just leave them blank and leave them as exercises for you. Yeah. Yep. So if lambda is equal to 0, we have no regularization. We're back to a linear model. Right? Because here, if lambda is equal to 0, this term right here and this term right here just disappear. Okay, what about when lambda is equal to infinity? Or a very large number. We can say if it's not exactly infinity, we can set it to like 1 billion. Yeah. Yeah, so Arham, you say that it's a straight line, and why do you say that?
Because all the parameters will be inherent. All the parameters will be near each other, all that data point.
Yeah, so all the parameters will be near each other. That's one way of thinking about it. That's good, I think. Another way of looking at it is if lambda here is really high, then as soon as theta becomes non-zero, you're going to have a huge penalty, right? So if lambda is like infinity, or let's say it's a billion, right? As soon as I set theta equal to one of the model weights equal to 1, then my loss will get really, really high. And when I try to fit the model using this loss function, the model will just favor setting all the model weights equal to 0. Okay, so if I increase lambda to infinity, I'm going to get a flat line. Flat line, all model weights equal to 0. And there's this change between L2 and L1 regularization. You can give me like a scowl if you think no, and a smile if you think yes. See some scowls? No. No. So this pattern right here does not change. So this is not the difference between L2 and L1. Okay, let's try another one. I do want to point out to you one particular thing about this regularization penalty, which is that we don't regularize the bias term. So if you remember, the linear model looks like theta sub 0 plus theta 1 times x sub 1, so on and so forth. We have theta sub 0 here, but this summation starts at j equals to 1. So we don't actually include the theta sub 0 in the regularization penalty. Why not? So think about this for a few minutes and talk with your neighbor. Okay. Any guesses? What does it mean? What does it mean to regularize the bias term? So an easy variant here is say, what if I accidentally include j equals 0 here instead of j equals 1? And I can ask you what happens to my model when I do that. And in fact, it probably will happen to you in real life. And I'll show you what happens. I'll show you how I avoided it on the code that I just wrote. Okay, so it's a little tricky. What happens if you include the bias term in the regularization is that the bias term, if you regularize theta sub 0, then your model will try to make theta sub 0 smaller. But that often doesn't really make too much sense because changing theta sub 0 doesn't affect your model's complexity, right? So if this x2 here happened to be like some column to the power of 10 in my original matrix, then changing theta sub 2 will impact the complexity of my model. But this theta sub 0 here, changing it to be a big number or a small number won't make my model more complicated. It'll just lift my model away from 0. Okay. So for example, let's take a look at this plot here. If I regularized the intercept term, then what will happen is this curve here will get pulled down towards 0. So we don't regularize the bias term because it doesn't add additional complexity to our model. And if we do regularize it, we'll kind of artificially give our model the constraint that we want our model's predictions to start at the origin. When it's okay for us not to start at the origin, it's okay for us to start with some bias term here. Okay, so okay, got one more question for you, which is, when we perform regularization, I normalize data. And by normalize, I mean I take my data columns, and for every column, I subtract the mean, and I scale the data to lie between -1 and 1. So I want you to figure out what happens if we don't do this. Okay, so stare at it for a few seconds. And if you have some ideas, turn to your neighbor and share your ideas. All right. So the intuitive reason why we normalize our data is because our data columns can have very different magnitudes. So if I have a column of, let's say like, if I have a column with number of days where I came to Evans, and I have another column with the number of people inside Evans each day, then the magnitude of those two columns will be very different. And what happens if I don't normalize the data is that my model will try to select parameters for the number of times I came into Evans and the number of people in Evans. And what's going to happen is that my model, if I don't normalize, will penalize the features with the smaller numbers more. Okay, so if I go back to my code here and show you, let me take my water, and I think if I do, let's take my ridge model, 12, and I think if I do transform on my x, doesn't have the transform, sad. Okay, I'm trying to wing a demo here, but it's obviously not working out. Let me try one more thing. Okay. Nope, doesn't work out. Okay. You can imagine with me that if I take my water level change and add degree 6 polynomial features. If I add degree 6 polynomial features, then I'm going to take every number here and take it to the power of 6, right? And those numbers will be very large. And because the numbers are very large, when I set model weights using linear regression, the model weights for the smaller features will generally be bigger than the model weights for the bigger features. Okay? And if I don't normalize my data, I'm going to enforce an artificial penalty on the features that just happen to have smaller numbers. Okay, so what's going to happen is if you actually don't normalize your data, you'll find that when you fit ridge regression, your model will look the same no matter what lambda or what alpha you set what lambda or what alpha you give your ridge regression model. Okay, so you can try it out, but it's a mistake that I've made many times, and I'm sure you'll make too. And the reason why I put the normalized equals true here is I want to tell scikit-learn to normalize those columns before fitting the model. The reason why I say include bias equals false here is because ridge regression in scikit-learn will add a bias column itself, but it will make sure not to regularize it. Okay, so if I include a bias term equals true, and I tell ridge regression not to include the intercept term, then what's going to happen is that ridge regression will put regularization on the intercept term as well. Okay, so you do have to be careful about what transformers are including the bias and when you put in the bias into your data matrix. Generally speaking, it's better to keep the bias out of your matrix until the very end, and then have ridge regression or lasso regression put in that intercept column for you. Do make sure to put normalized equals true, because I feel like the default is false. So the default for ridge regression and lasso regression is false, but usually you want it to be true. Okay, so artificial penalty on features with small numbers. All right. I have an exercise for you to take home, but you should be able to prove that if you take the ridge regression loss, the stochastic gradient descent update rule looks like this. Okay, so the procedure is relatively similar to the one for linear regression. There are some minor differences, and you should be able to, but you should still be able to apply the gradients to the loss and get out this as your final gradient descent update rule. You can extend this update rule to batch gradient descent, okay, and you can also extend this update to lasso as well. So you should be able to do both ridge regression and lasso. Okay, so after all that work, why do we have two kinds of regularization? So why do we do both L2 and L1 regularization? I can give you the intuitive hand-wavy explanation first, and I'll give you the more sophisticated explanation second. Okay, so the intuitive hand-wavy one is that when you use L2 regularization, you notice that in my demo, all the model weights were non-zero, even though some of them were really, really small. Right? So some of the model weights were like times 10 to negative 19, or times 10 to negative 20, which is, for all intents and purposes, equal to 0, but using L2 regularization will set them, so we'll keep them at above 0, but very slightly above 0. Okay. And so we tend to use L2 regularization when we think that we have many small factors that contribute to the outcome. And you noticed in my demo that L1 regularization will set some model weights equal to 0, depending on how big lambda is. So if I set lambda equal to a large number, there will be many model weights that lasso regression will set exactly equal to 0. And because of that, we say that if you use L1 regularization, you can also perform what we call feature selection, right? So it'll mark which features it thinks are completely useless, and because of that, we can select out the features that we think are important. Because of this trait of L1 regularization, it makes sense when we think a few major factors contribute to the outcome, as opposed to many small ones. Okay, so here's a more sophisticated explanation. So if we have a linear model with two parameters and no intercept term, then we'll have two parameters, theta1, and theta2. Okay, so I put theta1 on the x-axis and put theta2 on the y-axis. So if I go in the right direction, I'm going to increase theta1, and if I go up on the y-axis, I'm going to increase theta2. Okay, and now if I have some data, I can tweak theta1 and theta2, and when I tweak theta1 and theta2, my loss will change. Okay, so here I plotted theta hat as the best combination of theta1 and theta2, and as I move away from theta hat, I'm going to get a higher and higher loss. Okay, so here I plotted what I call a contour plot, and each of these contours here refers to a constant loss and the combinations of theta1 and theta2 that give that loss. Okay, so if the minimum loss is like 10, then here is the point at which the loss is 10, and then this contour here could be when the loss is 12, and this contour here could be when the loss is 14. And usually there are many combinations of theta1 and theta2 that will give the same loss. So that's why I draw these ovals here. These ovals here say that all of these combinations of theta1 and theta2 give me the same loss. Okay, now if I don't have regularization, what I'm going to do is run gradient descent. And you can imagine also that this right here is like a bowl that goes into the screen. Okay, so as I go closer and closer to theta hat, I go deeper and deeper into the valley of my bowl, and gradient descent will kind of like roll a marble down the hill until it gets to theta hat. Okay, now when I add regularization, I have two things that affect my loss now. I have my original loss, but I also have my regularization penalty. Okay, so when I add L2 regularization, I will add these contours to my contour plot. Okay, so the green circles here refer to the penalty incurred by regularization, by L2 regularization. Okay, so remember that regularization is the sum of the squares of theta1 and theta2. And so right here at the origin, when theta1 and theta2 are both equal to 0, I have no penalty. And when I increase theta1 and theta2, I increase my regularization penalty. And so what my model will do is it will not find theta hat, the original theta hat. It will pull my thetas closer to the origin because it's trying to balance the green circles and the red circles. Okay, so what's going to actually happen if I add regularization is that it's going to give me this point right here. Okay, and so theta1 and theta2 are smaller than they were before because they're pulled towards the origin. L2 regularization has circular contours for its penalty. And the reason why it has circular contours for its penalty is because if you remember the equation for a circle, the equation for a circle is x squared plus y squared. And in general, when I have the sum of squares, what I have are circular or spherical contours. Okay. Now, for L1 regularization, I don't have circles anymore. I have diamond-shaped contours. Okay, so these are the contours for L1 regularization. And the reason why these are the contours is because I'm summing together the absolute values of theta1 and theta2. So instead of squaring them and getting a circle, I'm summing them and getting linear piecewise functions here. Okay, and because they're linear, I get this sort of contour for the penalty for L1 regularization. And if you notice here, if I look at the point where the green diamonds intersect the red ovals, what oftentimes happens is that the green diamond will intersect the oval it'll intersect it on the axis because this part of the diamond sticks out the most. And when it intersects like this, when I apply L1 regularization, I'm going to say these are my final model weights, but you'll notice here that theta2 is 0. Okay, so because this green diamond sticks out more on the axes, if I happen to get a loss that intersects with the axes, then some of the model weights will be 0. And this applies in higher dimensions as well. Okay, so you can imagine here if I have like a 3-dimensional graph, then I might have like concentric like octahedron, I believe. It's a little bit hard to visualize, but the same basic idea applies to higher dimensions as well when I go beyond 2 dimensions. Okay. So, regularization gives us another way to manage the bias variance trade-off. Right? So if I increase lambda, I'm going to increase the bias of my model, but I'm going to decrease the variance of my model by decreasing my model parameters. If I decrease lambda, I'm going to have less bias and more variance. How do I pick lambda? I use cross-validation. Okay. So, talked about k-fold cross-validation, which is used to perform model selection. We talked about regularization, which gives us yet another way to manage model complexity. And in particular, it lets us add complexity to our models without overfitting. As usual, when it comes to these parameters, which we call hyperparameters, we use cross-validation to tune the model and perform model selection. All right, that's all I got for today. I'll see you next week.